Hello and welcome to the new podcast PLC2's Logic Lounge, the recently awarded #1 worldwide authorized training provider from AMD. Whether you are an engineer and working with FPGAs or you are a student embarking on your journey in hardware design, this podcast is exactly for you. Sit back, immerse yourself in the world of FPGAs, and listen to our conversation today.
Hello, welcome to PLC2's podcast, today on timing constraints. My name is Steffen Zimmermann, I'm CEO of PLC2 Design, and welcome again, Eugen. Good to have you here, talking about the specifics of timing constraints, something that I think differentiates hardware designers from software designers, although in programmable logic, VHDL is widely used as a programming language.
Yeah, Stefan, thank you very much for the introduction. I think you hit exactly the right point. Timing constraints are very different compared to software design, and it's very, very important for the FPGA designer to understand what's all about.
Okay, Eugen, let me start with the first question. Why at all does an FPGA engineer or hardware designer have to deal with timing constraints?
Yes, with the help of timing constraints, we can provide very, very precise timing information for each signal path in the FPGA. For example, we can define a maximum delay for signal passes from one flip-flop to another flip-flop, or we can even define a minimum delay from a signal passes from one flip-flop to another flip-flop, or we can define something in between. If such time information is missing, then the design software may make completely false assumptions on our design, and as a result, the design will not meet the performance, and in the worst situation, it will fail completely.
Mm-hmm. You were referring to the timing from flip-flop to flip-flop. Is this relevant only within the FPGA or also compared or with respect to other domains, external components, for instance?
Exactly. The term flip-flop, the flip-flops are not limited to internal to the FPGA. The flip-flop are also part of the upstream components, which are outside of the FPGA, or downstream components, which is again outside of the FPGA. So in this case, we are talking basically from register to register without the definition where are the register located. This means specification of the timing constraints can be divided in three classes. The first class we can define, as I already said, minimum and maximum delay from a path register to register. Or in the next class, we could define relaxed specification from one register to another register. For example, let's assume we have to transfer status information from one register to another register, but it's not so very time critical. We can afford to spend more than one clock cycle to transfer this information. So in this case, I can assign a so-called multi-cycle constraint. You have multiple clock cycles time to transfer the signal. Or, which is also a very, very advanced specification, we could actually, if delay time from one register to another register is completely not important, then we could define this path to be a false path. This means I don't care about the delay time. It could be even 1 microsecond. It could be today very, very huge time. So, but as a general statement, it is very, very important for us to specify the delay requirements on our design as exact as possible. That's the key.
Okay, yes, that really makes sense. Why, Eugen, would you want to specify a relaxed timing constraint? What would be the benefit of specifying a relaxed timing constraint?
For example, let's assume what is general a good idea. Let's assume we do have one clock in the system. So we are about to design a completely synchronous design. But even if the clock, let's assume, is 100 megahertz, I do have, for example, the requirements that a counter will run maybe at 10 megahertz instead of using a second clock. So this means instead of using a two clock domains, I still stick with 100 megahertz and spend an enable signal for this counter. This means this counter will not count every 100 megahertz clock cycle, but maybe 1 out of 10. So this means we have 10 clock cycle time to transit a signal from clock domain A to clock domain B. So this makes it very, very easy for the software to do the layout. We will get a very, very nice result, and this will also provide us a shorter turnaround time for the implementation.
Okay, so this means that when the timing constraint can be relaxed, can we say that the effort for the tool is less and that the area and resource consumption of the synthesized logic will be less?
Yes, exactly. This means the tool today will exactly understand the timing requirements, even if our timing requirements are very, very high. The tool, in this case the synthesizer, would be able to define and use parallel structures in order to gain the speed. But parallel structures in hardware means it is more hardware, so this means utilization of our device will be higher, the routing will be much tighter, the electrical power consumption will be higher, and the turnaround time would be less. This means it is always a good idea to relax the timing specification as much as possible to gain performance.
That's an interesting point. So if I already have an FPGA which is heavily utilized, so maybe the area consumption is already somewhere at 80%, what would happen if I have many hard timing constraints? What would the tool tell me or the tool chain tell me?
So the first observation would be it will take a very, very long time for the software to finish. And the software will try and try to get the best result, but it will fail. Then the software will report to me, well, I was not able to meet the timing for this pass, or this pass. Now it is up to the designer to look very, very closely to this pass and find the problem. What is the problem? Unfortunately, this is not always very, very easy. You need to have some talent of a detective in order to understand why is this pass actually failing. And again, let's say that the outcome of this observation is the designer must be very, very familiar with the design he's trying to optimize. If the designer has no idea what is the design all about, he has no deep knowledge of the design, he will never be successful actually to obtain and to get good results. He must understand the design. That's definitely the key.
Mm-hmm. So if we think of VHDL development and FPGA logic design as a software skill, what would happen if I don't really take enough care with timing constraints? If, let's say, in the worst case, I even ignore timing constraints and I'm just looking for function, what would be the worst case scenario that could happen in this case?
I'm facing this situation actually for several years. What the people are doing, they define the circuit, they run the functional simulation, it works very, very good, it's fine, but it's not a problem because the functional behavioral simulation is always a unit delay simulation. This means there is no timing information available, so it will, of course, work all the time. But then, and the designer is actually happy because the FPGA is working in the simulation. But now they actually don't define any timing constraints. They run the implementation. Because there are no timing constraints, the design software assumes, well, there are no requirements at all. So that's easy. And you get some results which doesn't really match your requirements, but you didn't define any requirements. Then you get your FPGA, no error at all, everything is successful, and you just load FPGA to your application. And now happens very, very strange thing. The FPGA is very, very sensitive to the environmental conditions, like temperature, like the voltage, like the process. So what may happen that in the lab, the FPGA is working. But as soon as you maybe open the window in the lab and it's getting a little bit cooler or warmer, the FPGA change the function and it will fail. And then the customer calling me and say, oh, the FPGA is broken. No, the FPGA is not broken. You didn't specify the timing constraint. Very, very bad situation.
Mm-hmm. Okay, so this is actually a matter of reliability then. The worst case would be that it looks like it's working, but when I deliver it to the customer and they maybe use it in a colder environment or in a hotter environment, it wouldn't work or only work in 90% of the time, something like that.
Exactly. And therefore, one of the basic steps in order to assure the quality is after you finish the design, you have to prove to the management or to the customer or whoever that you did first the complete specification of your design, and second, you run the timing analysis of your design, and finally, you get no errors and no warnings. And that gives you the proof, yes, my FPGA will work with all circumstances and will work at the best case conditions and then at the worst case condition, and of course in some intermediate typical cases. Yes, very, very important.
Okay. The constraints are actually something which helps the designer to find a design which is meeting all the requirements, including environmental conditions. So does these tools that the designer can apply needs to have models of the logic and the delays that are present in the FPGA?
Yes. So AMD, former Xilinx, they spent since the beginning a lot of time to characterize their devices very, very exact, and we will get all the information in form as a data sheet in the system. In Vivado or the design tool, whatever you are using, is actually reading all the information and will extract all the time information which is defined there. The vendor will guarantee the timing behavior of the devices, so you can be sure if the timing analysis tells you it will work in all circumstances, then it will work in all circumstances. Yes.
Mm-hmm. So we are on one hand side, we are heavily relying on tools and the capabilities of tools and correctness of models. But if I understand you right, it's on the other hand side important to have a certain skill set as an FPGA engineer. It's not good enough to know how to program in VHDL.
Yeah, exactly. That's definitely not enough. It is also not enough to be, let's say, a good software designer, because you need a completely different skill set. For example, the FPGA designer must be very, very familiar with the FPGA architecture he is using. He needs to know very, very in detail, actually, the internal FPGA structure in the architecture. Which components are available to me? Which components are inside the CLBs? Which components are inside the peripheral cells? And how can I use this very, very effectively? If I don't know, if I don't have this information, it will be very, very difficult for me actually to be successful. So in this case, I think that the demands on the FPGA designers are high, could actually be very high if he needs to do a good timing specification. He need, of course, to learn and to understand the timing concept methodology.
Mm-hmm. And that's something that I think you have taught in several trainings in the past. So if you would have to summarize the typical pitfalls that the customers or designers could get trapped in, what would you summarize are the most important aspects if I ignore timing constraints?
I think maybe the most critical would be I just use a synchronous circuit design instead of synchronous. Very, very dangerous. The second is I don't really deal good in terms of with the reset and the set signal and use asynchronous set and asynchronous reset. That's a big problem. And the next is I don't really understand which passes might be ignored very without any penalties. I'm talking about false passes. I don't need the time, the high speed between these two registers, for example. And of course, what's always a problem, I don't really think about the CDC. It's a clock domain crossing problem. And I think the clock domain crossing CDC is actually part of our next podcast.
Okay, yeah, makes sense. So I'm looking forward to that next podcast. Eugen, really, I enjoyed having you here and raising questions to a real expert in the field. Hopefully, you will have the chance to teach a lot more designers on timing constraints in the near future.
Thank you very much, Stefan.
Goodbye, Eugen.